Welcome back to the lecture series on analysis in state space. We have just moved from modeling in state space to analysis in state space. We have completed one lecture in analysis that was on solution of state equation. So before moving on to today's lecture, we'll just have a quick review of what we did in the previous lecture. If I have a state space model given by this equation, the well-known state equation and the output equation, then the solution is given by equation 1 and 2, 1 or 2. The difference between the equations 1 and 2 is that in equation 2, the time at which the analysis starts or the determination of x of t starts is taken as t naught is equal to 0. Okay, so that is the only difference between equation number 1 and 2. In both of these equations, we take this phi of t or we take e power at as phi of t. So e power at, we had a term here. That term was taken as phi of t. So we had two special cases also. What are the two special cases? The first case is zero input case and the second case is zero state case, or zero input response and zero state response. Zero input response is response of the system due to the initial conditions only. No input. So in that case, the solution is x of t is equal to phi of t minus t naught into x of t naught, or x of t is equal to phi of t into x of 0. Okay. So the other case is the response due to the input with zero initial conditions. So here we assume that the initial conditions are 0, but there is an input u of t. In that case, the solution is given by these equations 5 and 6. If we have both of this, I mean the initial conditions due to the state variable, initial conditions of the state variables, and also the input, then the total response is given by the equation 1 or 2. Okay. So here, if you take this equation number 4, which describes the case of a zero input response, then it is given by x of t is equal to phi of t into x of 0. So let me explain this with the help of a first order system. And if it is a first order system, obviously it will have a single state variable. So let me say I am going to take t in the x-axis and the state variable in the y-axis. It is nothing but I am going to describe how this state variable x of t is going to vary with respect to time. Let me say that at a particular time t naught, I am going to start my analysis. So let me say at this t naught value, the initial value is x naught. Now when as t increases from t naught, at t is equal to t1, let us say this x of t will have some other value. Let me say that is x1, okay, x1 of t, or I can say that x of t1, that's the right notation, x of t1. So how do I get it? This transition from x naught to x of t1 is described by this equation. X of t is equal to phi of t into x of 0. So here in this case, x of t is equal to phi of t into x naught. At t is equal to t1, x of t1 is given by phi of t1 into x naught. Please see this equation. To get the value of the state variable at t1, what I am doing is I am just multiplying the initial value x0 by a matrix phi of t1. Okay, so here the phi of t1, since it is a first order system, it is going to be of the order 1 cross 1. Okay, and if I multiply this, I get the new state. So this is the initial state and this is the new state. So new state is obtained, or the transition from the initial value to the new state is obtained by multiplying the initial value by this phi of t1. So that is why I call this matrix as state transition matrix. Okay, and all these equations which describe this transition from one state to another state, we call them as state transition equations, and phi of t, we call it as the state transition matrix. One important thing to be noted is phi of t is given by e power at, and obviously a is a square matrix of order n, where n is the number of state variables, and therefore e power at is also going to be a square matrix of order n, and therefore phi of t, or the state transition matrix, is a matrix of order n. So this is what we saw in the previous lecture. Okay, now the important term in the entire set of equations is this state transition matrix phi of t. This class we are going to focus a little on this state transition matrix. Okay, so what we are going to see are the properties of the state transition matrix and how I can evaluate the state transition matrix. Once we do this, we will just take up a problem, armature controlled separately excited DC motor. We will have its model state equation, and then we'll see how we can solve that state equation to get its solution. Okay, so that is what is going to be the content for this lecture. Just let us take the first topic, that is properties of the state transition matrix. Okay, properties of state transition matrix. Okay, so first property what we are going to look at is what is going to be phi of 0. Okay, so we know phi of t, the state transition matrix, is represented by e power at. Okay, so phi of 0, let us calculate. We know x of t is given by phi of t into x of 0. At t is equal to 0, when t is equal to 0, x of 0 equal to phi of 0 into x of 0. Please notice that this x of 0 is a vector which will contain x1 of 0, x2 of 0 up to xn of 0, where n is the number of state variables. Okay, so see, there is a vector. I am multiplying that vector by a square matrix. We already saw that phi of t is a square matrix, and therefore phi of 0 is also a square matrix. So I am multiplying a vector by a square matrix, I get the same vector. What does it mean? It means that this square matrix is an identity matrix. Therefore, phi of 0 is nothing but an identity matrix of order n. Okay, so phi of 0 is equal to in. So that is the first property. And now Let us see, if I have phi of t, if I take its nth power. Please note again, phi of t is a matrix and I am taking the nth power of this matrix. This I can also write it as phi of t power n. What is phi of t? E power at the whole power n. This is e power a nt I can write. Please note, here when I compare these two terms, here t is replaced by nt. That's all. So therefore I can write it as phi of, instead of t I have to put nt. I can write it as phi of nt. Okay. So that is what is the next property, phi of nt. The third property is, what is going to be the inverse of phi of t? Okay. Here it is same, I can even deduct from this. Here n is equal to minus 1, therefore obviously if I put, it is going to be minus t. This leads to another property. See, if I have phi of t, that is the state transition matrix, to get the inverse of the state transition matrix, what I need to do is just replace this t by minus t. That's it. Okay. Therefore, if phi of t exists, phi of minus t also exists. That means for every state transition matrix phi of t, there exists an inverse. What it means? Phi of t is always non-singular, because only for non-singular matrices you will have the inverse existing. Then the fifth property is phi of t1 plus t2 is equal to, let us say, it is a power, instead of t I have to put t1 plus t2. This I can write it as e power a t1 into e power a t2. What is e power a t1? It is nothing but phi of t1, and this is phi of t2. Okay, so altogether I can write it as phi of t1 into phi of t2. Okay, so these are the 5 properties of the state transition matrix. So having understood the properties of this state transition matrix, let us try to evaluate it. I have rewritten the solution of the state equation here, assuming that t naught is equal to 0, and we all know that this equation we derived analytically from the state equation. Okay, so in this process I came across this state transition matrix, and this is a matrix exponential. The problem is this matrix exponential e power at. In mathematics, this is computed like this, by an infinite series. I e power at is equal to identity matrix of size n, and then it is at by 1 factorial, you need not write it as, then at a square t square by 2 factorial, and this goes, it is going to be an infinite series k by k factorial, it goes on. Okay, so that is how it is computed in mathematics, and it will be interesting to note that this, even though this is a infinite series, the series will converge for any square matrix A and for finite time t. Okay, for any finite time t. So therefore, the computation of e power at is not that straightforward. Okay, even though it converges, it involves some lot of mathematical computations. So we want to explore whether I can compute e power at in some other way. So what I'm going to do is I'm going to solve the same state equation using the Laplace transform, and I'm trying to find out whether the solution obtained through the Laplace transform is going to help me in computing this e power at. So let us try to get the solution of state equation through Laplace transform. Okay, the state equation is x dot of t is equal to ax of t plus bu of t. Let us take a Laplace transform. This is going to be this is a first order derivative, therefore s into x of s minus x of 0, the initial condition, a into x of s plus b into u of s. I can take this to this side, s x of s minus a x of s is equal to x of 0 plus b u of s. Clearly, I can take this x of s outside. When I take this x of s outside, I will get an identity matrix here. This was well explained in previous lectures, how I get this identity matrix, especially in obtaining the transfer function but from the state space equation. So in the same way, I can write like this, equal to x of 0, x of 0 plus b into u of s. Okay, so I want to have only x of s here. So the better thing is to pre-multiply this entire equation by xi minus a inverse. If I multiply, I will get si minus a inverse, here also si minus a inverse. Okay, so therefore here inverse and this matrix will result in identity matrix. This is the expression for x of s. From x of s, if I want to get x of t is nothing but inverse Laplace transform of x of s. What is that? Inverse Laplace transform of this entire thing. I minus a inverse x of 0. This is the first term, and the second term is inverse Laplace transform of si minus a inverse into b u of s. Okay, now compare this equation and this equation. This should be the same, right? Both are the solution of this state equation, therefore this should be same. So I can compare this first term and this term. So just remove all these things now and just retain only the last equation. Okay. Okay. So this is the same as this equation. So can you write phi of t into x of 0 is equal to inverse Laplace transform of si minus a inverse into x of 0. Please notice that x of 0 is the initial conditions. It is a vector of constants or numbers, the initial values of those state variables. Since this is a constant, there is nothing wrong if I write it as x of 0. Okay, so therefore what do you mean? Phi of t is equal to inverse Laplace transform of Si minus A inverse. Okay, so this matrix you are already familiar. This is what is the matrix you calculated when you found this transfer function from a state space model, and therefore you can easily find this. So once you find this matrix, if you take the inverse Laplace transform on that, you get the state matrix phi of t. So one more interesting thing is, I can take a Laplace transform on this phi of t also, then it is going to be phi of s is going to be Si minus A inverse. Si minus A inverse, I can write it as phi of s also. Okay, so what is important is I got a new method, or I got an easy method to calculate the state transition matrix rather than this infinite series method. And also I got a solution x of t in terms of the Laplace transforms. So we have understood how to find out the solution of a state equation in time domain or through the Laplace transform, and you can find out the by finding this phi of s and phi of t, you can find out this solution. So now it is a time to apply these things, okay, to a problem and to get the solution using this method. So we take up an armature controlled separately excited DC motor. So this is the schematic of the system, and using the principles what we learned in lectures 1 to 4 of modeling in state space, we can get these differential equations. I am not going to explain how we will get it. These things have been already covered in previous lectures. I just leave it. So I don't take those modeling aspects again. So anyhow, I get this differential equations. So let us have a look at the notations used. Omega t is the angular speed of the rotor. Ia of t is the armature current, and Va of t, that is this one, is the input voltage. Kt and Kb are the torque constant and the EMF constant respectively. Okay, so here these are the differential equations. Now there are two variables that are going to change with respect to time, omega of t and Ia of t. So we will define them as the state variables, and the input is this Va of t. We will take it as u of t. The input u of t is Va of t. So with this definition, I can rewrite this differential equation as this state equations. Okay, so therefore this is the state equation representing this system. Now we will assign some values for these parameters. Ra, we will take it as 1 ohm, La is equal to 0.1 Henry, J is equal to 0.1, B is equal to 0.1, Kb and Kt is equal to 0.1 again. So if I substitute these values, this is what is the state space model of the system with these numerical values. So now I have to solve this state equation to get the values, get the expressions for x1 of t and x2 of t. So that is my objective. Okay, so we will solve it. So when I solve it, as we have already seen, I'm going to solve it for three conditions, three cases. The cases are these. The first case is zero input with initial conditions. That is only initial conditions. The second case is only input, no initial condition. Third case is both input and both input and initial conditions. Okay. So the initial condition what I have taken is x1 of 0 is equal to 1 and x2 of 0 equal to 0. So that means x1 of t, what we took it as this angular velocity. So when I switch on this input, I assume that, or the rotor is already rotating. Rotor is already rotating at a speed of 1 radian per second. That is what it means. Okay, so that is what is the initial condition. So with this initial condition, and for three different cases, let us solve. The first case is, as I said, zero input, only initial conditions. Input is 0, that means v of s is equal to 0, and the initial conditions are 1, 0. So we know the solution is this: x of t is equal to phi of t into x of 0. So that is nothing but inverse Laplace transform of phi of s into x of 0. That's what we saw just now. And it is inverse Laplace transform of si minus a inverse into x of 0. So obviously, if I calculate this or take an inverse Laplace transform, I get the solution. That's it. So we have to calculate this first, si minus a inverse. So that is what is phi of s. This is what is a. Si minus a, we are already familiar with such things. So S inverse of Si minus a is subjoint of Si minus a divided by the determinant of Si minus a. Adjoint we know to calculate using the transpose of the cofactor matrix. This is the cofactor matrix, and we took the transpose, we get the adjoint, and the determinant of this is this s plus 1 into s plus 10 plus 1. So you get this determinant of this matrix as this. So this is a quadratic polynomial. This can be factored like this. Up to third order quadratic polynomial you can factor using your calculator. That is, find out the roots of that equation, and using the roots you can factor this polynomial. So it has been done. So now the inverse is nothing but adjoint by determinant. Adjoint is this. This is determinant. So we got Si minus a inverse is what is our phi of s. Okay, so once I get this, I have to multiply with x of 0. So that's what I'm doing. This x of 0 is initial conditions are already given. Okay, so if I multiply with this x of 0, so s plus 10 into 1 plus 1 into 0. That means I'll get only s plus 1, and similarly I will get minus 1 into 1 will be minus 1, s plus 1 into 0 will be 0. So therefore I will get only minus 1 here, and therefore this product is s plus 10 at 1. It is going to be a vector. So I got this x of s into phi of s into x of 0. Okay, so now I can take this determinant inside. This is common for all the elements. So all the elements s plus 10 and minus 1 are divided by this s plus 1 plus 125 and s plus 9.8875. Okay, so I got this. Now the only step is to get the inverse Laplace transform. Okay, so the next thing is we have to find out the inverse Laplace transformation. So to find out this inverse Laplace transform for this, it is necessary to find out the partial fractions of this rational expression. So I can find out this, there are two simple factors here in the denominator, and therefore I will have two residues or two constants a and b in the numerator. They can be found, so they have been found, and that is applicable to this rational expression also. So both these rational expressions are represented as partial fractions. Now once I find the partial fractions, I can just simply take the inverse Laplace transformation. Inverse Laplace transformation is this. For example, this is a constant 1.1, 1.012, and this is 1 by s plus a, where a is equal to 1 plus 1125. That is, the inverse Laplace transformation is e power minus at. Okay, so e power minus at. So similarly, I get the inverse Laplace transform for the other terms also. So now this is the solution. This is the solution. X of t, I got the solution. That's it. So obviously x of t has got two values. So one is x1 of t and the other one is x2 of t. x1 of t we took it as the omega of t, and x2 of t we took it as the armature current. So these are the expressions. We got the solution. This is only with the initial conditions. Now the second case is no initial condition, but there is an input. I'm going to take this input as the unit step input. Okay, so unit step input, which will have a Laplace transform of 1 by s. So the solution here is given by x of t is equal to inverse Laplace transform of I of s b into u of s. Phi of s is nothing but inverse of si minus a, that we have already found. We have to multiply with b and u of s. B is here and u of s is 1 by s, that is 1 cross 1 matrix. So if you multiply again, this is what you will get. Now you can take this inside. Yes, take it inside. There are three simple factors. Okay, so now I have to use again the partial fractions here. So I will get three partial fractions. So once I resolve into partial fractions, I can take the inverse Laplace transformation. So this will have an inverse Laplace transform of 0.9094 and so on. It's well known, nothing to explain. And now this is the solution, x1 of t and x2 of t. The first term is x1 of t and the second term is x2 of t. Please notice this is the solution with zero initial conditions but with step input, unit step input. Then the third case is total response. We assume that there is input, also there are initial conditions. That means the rotor is rotating as 1 radians per second, okay, without any energy given into it, but it is rotating because of the energy stored in the rotor due to its inertia. And when it is rotating at 1 radians per second freely, the switch is on. That is what it means. A unit step input is applied to the system. So that is a scenario. So now let us try to get the solution of x1 of t and x2 of t. It is the sum of these two. Okay, so we have separately found out the solution. Now we have to add these two solutions. I will get this. Okay, that's very simple. So response due to the initial condition and also the response due to the input. Since this is a linear system, I can superimpose and get the result. So this is what. So I got the results for the variation x1 of t and x2 of t for this condition also. Okay. So what we did in this lecture, we understood that if I have a state space model like this, I can get the solution like this. And the new thing what we learned in this lecture is that this phi of t I can represent in terms of Laplace transform. Okay, so the Laplace transform of phi of t is phi of s, it is nothing but inverse of si minus a. So using this, I can easily compute the x of t. Okay, so also we learned about the properties of the state transition matrix. So these are some of the properties that we looked at. Phi of 0 is equal to identity matrix. Inverse of a state transition matrix is phi of minus t. Just replace t by minus t. and other things as given here. Then we took a problem and we understood how we can get the solution from the state equation. We took the case of a armature controlled separately excited DC motor, and we get what the solution. The procedure is like this. First find out this phi of s, that is nothing but Si minus A inverse of Si minus A. Then you get the product of this phi of s into x of 0 and phi of s into b into u of s. These two products. Why I have included and or is that depends, so depending upon whether you are going to take only the initial conditions or this input also. Okay, and once you find out these products, it's simply taking up the inverse Laplace transform on these products. Take the inverse Laplace transform, you will get the solution. Okay, so this is what we have seen in this lecture, and we modeled a system, we got the solution of the system also in state space. Now in the next lecture we will see some more analysis in state space that can be done. For example, the stability analysis, the controllability and observability.